Okay, so yesterday we began looking at what integrals really mean, different ways of interpreting them, and the basic stuff that will go into the fundamental theorem of calculus coming soon. So if you're watching the video, you should have the fundamental theorem of calculus and Riemann sums handout in front of you. So you guys were tasked to find the midpoint approximation for that 9 minus x squared function using 6 rectangles. What was that? Can you guys tell me? What was m sub 6? 18 something. Okay, great. So we're going to now do probably a more sophisticated one. Now you guys aren't going to be expected to really do this too much, like in your assignment or on the AP exam or anything like that, but it's an interesting prelude to more advanced mathematics, so I thought we'd do it anyway. So it says, part B on the second page of the handout. Suppose delta x sub k has equal width 0.5, okay, same thing we've been doing. Choose a random value for x sub k in each interval and compute the area of each Riemann rectangle that way, and let's just use 6 rectangles again. So I think our calculator has a variety of random number generators that we can use. So I gave you a hint on the handout that says use random integers. I'm not sure if that's what we want to do, because what we want to do is on the interval 0 to 3, we had some edges, right? The first edge was what? 1/2. The next edge was 1. The next edge was? The next edge was? Next edge. And last edge. So we approximated the area under that curve. You can do this the same way for any curve, yeah? We did it by using the left edges, we did it by using the right edges, and we did it by using an x value in the middle and tracing that up to find the y value. You can, of course, also do other more sophisticated ways of picking that to get a more accurate approximation. One of those ways is to randomly pick the x value and trace it up to get the height of the rectangle. So just randomly picking there. And then, see, as a human being, though, it's never random. And then picking there. And then picking there, and then picking there. But as a human being, again, it's never really random. Now a calculator's random number generator, if you took stats already, you learned that that's not really completely random either. It's got some kind of seed that starts the algorithm somewhere. But it's much more random than just going there, there, there. So let's try to figure out a way to pick an x value in each one of these locations using our calculator, okay? So I think if you go to Math, and then you go over to the Probability menu, you'll see some random guys. These are different random functions your calculator has that do different things. I don't even know what they all do. I'd have to experiment with it. First one's random integer. The next one's a random number. This says random bin. I'm not really sure. You can experiment with them. So let's try this with random integers. So I said pick a random integer between 0 and 10. Let's think ahead a little bit. Do we want to pick a random integer between 0 and 10 if we're going to stay inside each one of those bins?
0 and 3.
0 and no. Think inside each bin. 0 and 5. Let's try that. Did it work with a decimal, Kylie?
No, it doesn't work with a decimal.
So I'm going to say 0 and 5. And you can pick them one at a time, or how many random numbers are we going to need for this?
6.
6. So there we go. There's 5 random numbers. If you press it again, you'll see it generates a different list of 6 more random numbers, and so forth. So I'm sure yours are different than mine because the seed in your calculator is probably different than mine. So I'm going to use this one.
Yeah, we have the same seed.
Oh, do we? That's because our seeds are different. So you can actually randomize your calculator by doing a seed thing. I'll show you how to do that in statistics, though, if you guys haven't already taken it. Okay? Does anybody remember how to do that?
It's
been a while. We go to Math, and you store something, right? So pick your phone number, the last 4 digits of your phone number. Here's mine. And you hit Store, which is on the bottom left, and you store that in this random thing, and that'll make my random numbers start a different place than yours. So now if you go up and do this again, yours should be totally different than mine unless you use the same seed as me, but that's not a big deal. So anyway, I'm going to use these 6 right here. So how am I going to use these 6? Well, I'm going to use this 4 as the decimal place. So I'm going to say that the first x value I use is I heard it, 0.4. And the next one I'm going to use is 0.5 plus 0.5, so I'm going to be using the edge over there, 1. And then the next one is going to be 1 plus 1, which is right here, 1.1. And then I'm going to use 0.4 plus 0.5 is 1.9. And then I'm going to use 0, which will be, did I skip one? Oh yeah, see. So I got that interval, I got that interval, I got that interval, I got that interval. I got this interval is going to be at 2, and the next interval is going to be at 2.7. This is only one way of doing this, right? There's all kinds of other ways you could do this. Could you be more precise? Because this only lets us pick with 5 slots in each bin, in each subinterval. How could you make it pick with a smaller subinterval size? Think of a way we can use this same thing. There's a way. You could go and use random integer. Let's pick a random integer between 0 and, be more precise, make your grid more fine. Kylie has it. 0 and 50, or 0 and 500, or 0 and 5,000. That would make this much more precise, and then we could add that decimal place onto each little starting spot. Does that make sense? And we could generate 6 of those and fit these guys. So our first number would be 0.035, or excuse me, 0.35, and then 0.74, and then 1.29, and then 1.77. You guys see how that would go? So that's just another way to do this. Anyway, so I'm going to use what I had there, and I'm going to go through and create my random approximation. Let's see how close it is. So we can check ourselves with the right answer, by the way. So I'm going to go stat, edit, and change these around. So I had 0.4, and then 1, and 1.1, 1.9, and 2, and 2.7. There we go. And then remember our function was 9 minus x squared. These stay the same. I'm going to multiply the length and width of my rectangles over here. And I'm going to sum them up. Now, the approximations we had a second ago, we had an overestimate, an underestimate, and for that problem, the midpoint, I'm guessing you guys could guess, is the most accurate so far. How close is this to your midpoint approximation?
Exactly 0.3.
It's pretty close. So I'm guessing the real exact answer, which there is a real exact answer, which calculus provides, so we haven't done any calculus yet, exists. That has to do with integrals. So let's use, on our calculator for the first time, the calculator's numerical integrator, which will give us the real, God's answer, the area under the curve. Maybe that's it. We could have gotten lucky. So you go to, let me clear this out. Oh, what was it? Did you guys write it down?
18.3.
So let's say, call it our random sub 6. It was 18.365. What was the midpoint one? Because that one was probably pretty close too. Like that? Okay. Now, the calculator's numerical integrator, which is not the world's best numerical integrator, it fails in all kinds of cases, but it'll work on basic stuff like this one. You can go to Math, and you go down, and it says N derivative, that's the numerical derivative, I think we've used that before. This one is the numerical integral. Now, if you have a new calculator, it's going to pop up the integral. If you have an old calculator, it might say FN int. So, What the integral is, we'll discover, is the area under the curve from wherever we're starting. Where did we start? 0. So this is not an indefinite integral anymore. Now it's a definite integral. We're finding the area under the curve from 0 to 3. What do you think you put right here? 9 minus x squared. And this is just notation, but important. dx. And this is the calculator's way of doing it. The answer is 18. So which one was the most accurate approximation out of the ones we tried? The midpoint one. Now, if we did the random one and we made the grid finer, it might do better. What would be another way to make the random estimate for the area better? Think about
more
this.
rectangles.
Decrease the bin size. Oh yes, use more rectangles. Wouldn't that also make the midpoint more accurate? And even the left and right hand sides? What would be another way, if you're going to do it randomly, to increase the accuracy of this? And you have to stay with 6 rectangles. I could have you guys all do your own seed. You could all get a different random estimate. And then we could take an average. I bet that would be pretty darn accurate if we did enough sample size. What was the rule of thumb in statistics?
37.
And it's greater than or equal to 30. Yeah, yeah, 30. So, there's some different approximations. Let's move on to the next slide. So if you're watching the video right now, I think you want to try to find on number 2 on the 3rd page of the handout, f of x is now the exponential function. 3 to the x, I'm going to do the interval -1 to 3. Do part A. Find the left-hand approximation with 8 rectangles, the right-hand one with 8, and the midpoint with 8. Do it quite fast. See how fast you guys can do it. I'm going to give you like 2-3 minutes. You guys are like, what? 2-3 minutes? It's crazy. It should take 2-3 minutes.
Can we do it on calculator?
Yeah. All right, so let's look at that new problem. We're evaluating, trying to come up with the area under the exponential growth function 3 to the x, and we're doing it from here to here. So when you do it with 8 rectangles, I don't think it's super hard to just figure this out. So 8 rectangles, if you did 4 rectangles, the edges are like going to be every 1 unit. 8 rectangles is every half unit. So drawing it might not be necessarily essential on that one. When you get down to 20 or 40 rectangles, it becomes much more difficult to figure those things out. Hence, you need a little bit more sophistication. So I'm going to do L8, R8, and M8 really fast here on my calculator and see what I come up with, and you guys can check your answers. If you're watching the video, you want to make sure you try these yourself first. So I'm going to go Stat Edit. List 1, I'm going to go -1. Those are my left-hand edges. Going to go 3 raised to the list 1. My interval sizes are 0.5. I need to fix and make sure I have them for every list, though. There we go. Lists are all the same at level. So now I'm going to do the area. Go list 2 times list 3. Oh, I did it in the wrong spot. There is the left-hand approximation.
Oops.
Now let's do the right-hand approximation. So I'm going to go to list 1 and delete that first guy and go way to the bottom and put in my right-hand edge at the end. Need to redo these. Function was 3 raised to the x. These stay the same. Rectangles, base times height, or whatever. There is the right-hand approximation. Unless I made a mistake, I was going pretty fast. And now the midpoint approximation. Go back. I'll just delete this. This. The first midpoint I think is going to be what, guys?
-0.75.
7.5 and then
-0.25, 0.25, 0.75, 4.25.
There we go. It's in the middle. That's looking good, right? I'm going to go 7, 1. All right, so if you pictured this function, it's not always a guarantee that the left hand is the overestimate or vice versa. You've got to look at the picture. It depends on the concavity of the graph, whether which one is the overestimate or the underestimate. But we know this is probably the most accurate. Midpoint is usually better than left or right. Okay. Now let's do an even more accurate one by using more rectangles, like Katie and Derek suggested a second ago. So let's do the midpoint over again, but let's use 20 rectangles instead. So this is where you might want to first think about how big your rectangles are using a little picture. Okay? So how long is our overall interval? 4. So we're going to have to take 4 and divide it by how many rectangles? 20. What is 4 divided by 20?
1/5.
That comes out to 1/5, which is 0.2. So that's the new width of the rectangle where the x value should be. What is that?
So like,
That's the width of each rectangle. Now we're going to have 20 rectangles and each one is 0.2 wide. And you're going to have to draw all of that out. I suggest just drawing the first 2 spots. Okay? So we're doing a midpoint approximation, right? So if I draw, and I do it exaggeratedly big, so let's pretend that 3 is way out there somewhere. Okay? So here's the first edge. Where's the next edge going to be? Negative 0.8. So that means the first midpoint that you're actually going to use is what? Negative 0.9. What's the next midpoint that you're actually going to use? Negative 0.7. Maybe we should do one more of these because this is negative 0.6. Does that make sense? So I think once you've got the first couple, that should be enough to do it for yourself. And we're not going to enter all 20 points in our calculator without using a loop. So let's actually use a loop to do this. Okay? You can, of course, do it by hand, but that's not the lazy way. I'm taking the lazy way. So I'm going to go back to my lists. Just going to go ahead and delete out all these other ones. And in list 1, I'm going to go to the header, and I'm going to tell it to create all those midpoints using a sequence. So I think we saw sequence. Did you guys remember seeing sequence in your list operations? Second list. There it is. Sequence. This is kind of like a for loop. So I need to create a sequence that does those red points. So the first point in the sequence we want to be negative 0.9. So I'm going to say negative 0.9. There's different ways to do this. And then I'm going to press X for a variable. Or should I press X? You've just got to create a sequence which will generate all those red numbers. I think it's starting at 0.9 and then I have to add something each time, don't I? What do I have to add each time to get to the next red number? 0.2. And if I add it each time, I should probably put an X on that. And then you've got to tell it what variable you used, so put a comma and an X. And then you've got to tell it how many to do. And I think you have to tell it a start and a stop number, just like a loop. So our start number, if we want it to be 0.9, should we start with 1 or should we start with 0? What are you going to put here to make it start as 0.9? To start at 0. Now you guys tell me, if you're using 20 midpoints, you're going to have to count from 0 up to what number?
2.9.
How many? We want 20. So do you go 0 to 20? 0 to 20 is how many numbers?
21.
21 numbers. It's 0 to 19. And boom! There they all are. Doesn't matter how many there are in this list. So, you can go back. This is in my video now, so I'll load it up. So list 2, what were we supposed to do with each one of those midpoints? I don't think this has changed. 3 raised to the x. Those are all done. And how wide was each interval here, guys? 0.2. Now you could enter 0.2 20 times. I don't want to. So I'm going to do a sequence again. And I'm going to go back to sequence. Oh God. Up here, second list. Going back to my sequence. Now this sequence is the most boring sequence imaginable. It's just 0.2. I'll tell it X even though there's no X. And how many of those? 20. You could go 1 to 20, 0 to 19. I'm going to just go 1 to 20 this time. See if that works. If it doesn't work, we'll know. Ha ha ha. Let's go down to the bottom and make sure it looks good. Looks good. They all look the same size. And now I can do list 2 times list 3 and do the same thing we've been doing. There's a much better approximation. Now, let's do m sub 40. So if you're watching the video, I recommend you pause it right now and try to do m sub 40 yourself, and then check it with my work in a second. All right, so let's do the 40 rectangle midpoint approximation. So I'm going to redraw. So this time we're going to use 40 rectangles. More rectangles should mean more accuracy. So first I need to figure out how big my rectangles are, how wide they'll be for the base. There's going to be the length of this interval still 4. Now I'm dividing by 40. That's nice, that comes out to a 1/10, which is 0.1. So that's how wide each of my subintervals will be. So my first subinterval is going to go from -1, 1/10, to -0.9. My next subinterval is going to go out 1/10 to -0.8, etc. You don't need to draw them all. Just draw until you can find the midpoint or the left-hand edge or whatever. So what's in the middle here? Use common sense. It's going to be -0.95. This one's going to be -0.85. Once you've got the first 2 items in your sequence, I think that it's pretty easy to generate the rest. So, now I'm going to go to my calculator. I'm going to go to my lists. I'll go ahead and clear some of these out. All right, so I'm going to generate a sequence. And my sequence. Now, if you get the menu on your calculator that's user-friendly, it says like expression. The first thing you enter is the expression, the sequence expression. So our sequence needs to start with -0.95 for this one. And then I'm going to add how much each time? 0.1. And since I'm doing it each time, I'm going to put the variable there. I'm going to tell it what variable I'm using. And I'm going to tell it where to start the sequence and where to stop the sequence, because it can start and stop anywhere. If I want the first term to be -0.95, I better plug in a 0 here. So I'm going to go from 0 up until, how many rectangles do we want? Oh yeah, we wanted 40. So I'm going to go 0 to 39. And there is the entire list of midpoints. And now I'm going to go to list 2. Tell it to find the height for each one of those, which is 3 raised to the x for this function. List 3, I'm going to tell it I want each of the bases of those rectangles to be 0.1, so I'm going to do another sequence. Tell it my expression is just 0.1, give it a dummy variable, tell it to do 40 of those. You can go 1 to 40, however you want, you know. If you want to do a quick check, go up, and it'll bring you to the very bottom, and you can see they're all level, so I'm not going to have any issues. And then I'm going to say the bases are in, the heights are in list 2, and the bases are in list 3. There's the area of each one, and then I'll go sum them up. going to write this out to more decimal places this time. And there we go. That approximation is probably better. Let's use the calculator's numerical integrator to do this one. I'm not sure if the calculator could do this one exactly, or if it's using some kind of approximation. See, it's got to make those decisions just like humans do. So I'm going to go to math. It's math 9. From -1 to 3. I wanted to integrate 3 raised to the x power. Now there's a even more accurate version. But you can see how close these were. Extremely close when we used 40 rectangles and didn't use calculus. So. Okay, so we know some different ways to start thinking about these integrals now. We can use a variety of approximations with rectangles, right? But now I just want to start thinking about the actual calculus. So we could do each one of these with our calculator now as well, right? Get the exact answer if there is one. So that's a good way to do them. Let's try to sketch what each one means. We learned that this means area under the curve. So between 0 and 2, what's the area under x squared look like? Well, it should look something like x squared between 0 and 2. That guy. I don't think we could use geometry or anything like we'll do tomorrow to evaluate that integral, because that's like a bent part. There's a bent part on it, right? So we'd have to use these rectangle ideas we've been studying. Unless we had our calculator. Do it in your calculator, please, really quick. Use it, math 9.
2.666.
Is it exactly like 2.66 repeating?
Yeah.
Is that what you guys got?
I don't know if you.
Okay, it's positive, that makes sense. Let's do the next one. So now it says go from 0 to -2.
Oh, I didn't.
So you want to draw these. So we're going to think about the geometry here. So x squared, there we go. We're going from 0 to -2. It's like going from there to there. That's going to be this area, right? So do that one in your calculator, see what you get. So you got -2.666.
We have negative.
Okay, and then try this one. This one as a picture means go from -2 to 0,
I got 2.6.
which is that same area as a picture, but your calculator gives you a different answer, doesn't it? What's it say?
2.
From symmetry, these are the same, right? From the opposite sides of the parabola, we went out the same distance. So I think it makes sense that these are the same from the symmetry of the parabola. Why is that one negative? Because these represent the same picture. Because the integral is not going from left to right here. It's going right to left. It's going backwards. So you should write a note to yourself on your handout that if you ever integrate backwards, what do you have to do? You have to negate the area. That produces a negative area, whether it looks like it or not. You're going backwards, and going backwards is going backwards. I think that's negative. Okay? So we can, of course, do this with any function. So I picked something, well, excuse me, Mr. Peterson picked something simple, another simple function, sine of x. So he said, first let's look at between pi and 2 pi. So I'm going to do a sketch, sine of x, looks like that, right? So between pi and 2 pi is this part, isn't it? So why don't you guys do that in your calculator and see what you get. And your calculator should be in what mode here, by the way? Radian mode. I'm going fast, I know.
Oh, wait, what? Dang it.
So pi to 2 pi, how much is this shaded area right here according to the calculator?
It's about -2.
About -2? Yeah, it should work out to exactly -2 on this one. All right, so let's get all the answers and pictures first, and then we'll try to reason through why that's happening. Okay, so between 0 and 2 pi is that same picture, except we're shading in all of it. What's your calculator say that one is when you add up those two areas? Should say that. And this one,
Probably 2.
Katie says probably 2, so it says go from pi back to 0.
Negative. But,
I think the answer should be negative 2.
but we have to negate it because it's backwards.
And then what if we're going from 2 pi right here back to pi? You can confirm this with your calculator, but the answer should be,
Negative.
Ben is saying 2. I agree. Why?
Because it's showing negative for Because it's double negative.
Because it's a double negative, exactly. This first example should have told you that if you integrate any curve and the area is below the x-axis, that area is considered to be negative area. This example confirmed that because symmetry says these are the same thing, right? Whatever the area is, if that area is 2, then this area is 2. So if that area is negative 2, this area is positive 2, so they come out to 0. This guy went backwards from here to here, so even though it's positive 2, it's positive 2 backwards, which is negative 2. And then here you've got underneath, which is negative, and backwards, which is negative, so it becomes positive 2. So the two notes you should have now are, if you integrate backwards, the area is negative, and if you integrate underneath, the area is negative. And if you have a combination, you've got to take the net. Okay? So I don't think any of those ideas are revolutionary, but so now you know how to approximate integrals using different kinds of summations, right? We did left, right, midpoint, and random. And you know how to use your calculator's approximator to get the right answer most of the time. We still don't know how to do that with calculus, though. We're still relying on numerical, not calculus stuff. Okay? We'll see that coming soon.